Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. For Chapter 1 Digital to Analog Converter Circuits. Okay, before we go through on digital analog circuits, so this is some introductions of analog signals. So the analog is a continuously valued signal such as temperatures, speeds with infinite possible value in between. So physical parameter seperti temperatures, speeds, value ni adalah value yang sentiasa berubah. Okay, dia boleh berubah dan dia ada value-value sendiri. Okay, jadi dia adalah continuous dan directly measured quantity in terms of some other quantity. Dia adalah yang biasanya kita measure, yang kita boleh measure quantity ni. For example, temperatures for thermometers. So the mercury, perubahan mercury tadi akan menyebabkan perubahan temperature lah. Okay. Jadi dia tidak melibatkan 0 dan 1, dia melibatkan certain value. For example, daripada berapa 0 kepada 5, so dia ada 0,1, 0,02, 0,3, 0,4, 0,5 until 5. And then for speed in car speedometer, so the needle move, okay, to show the accelerations. Okay, and then for the stereo, the volumes increase as you turn the knobs. That is the analog signal. It means that they have a range of values. Okay, and then for digital signals, is discretely valued signal such as integers encoded in binary. Okay, in digital signal have only 2 stages. Okay, for digital computer we have referred to binary state 0 and 1. So 1 is on and 0 can be off. Okay, for example, a light switch can be either on or off. The door to a room is either open or closed. So digital signal ni refer kepada 0 and 1. Okay, so that's why we call it digital signals. Okay, for ADC and DAC. ADC or analog to digital converter take the analog values or analog voltage or currents, okay, as an input and produce the digital code as an outputs. This digital code is proportional to the analog inputs. Okay, that for a ADC. Okay, and then for the DAC, DAC take a digital code, dia terbalik dengan yang ADC. They take a digital code as an input and produce the analog voltage and currents as its outputs. This analog output is proportional to the digital inputs. Okay, so dia terbalik lah, input pada analog pada digital for ADC and digital for the analog for DAC. Okay, this is for the general overview or general understanding of ADC and DAC. Okay, for example, we have a physical signal here or physical variables here. Okay, so for example, physical, kita ambil temperature, for example, temperature. Okay, we have temperature as a physical variables. Also, and then we have transducers or sensors, okay, to sense the temperatures. Okay, so the value of temperature is ranged from, for example, from 0 to 30. Okay, so there is an analog so they have analog inputs. Okay, because of our computers only understand on digitals. Our computer only understand 0 and 1s, machine language. Okay, so we need to convert this analog signal kepada digital by using ADC converters, and then the outputs here, the input here for the computers become digitals, and then they do some process here. Okay, process. Okay, they do some process here. Okay, for example, conversions or what, and then they want to move something. For example, they want to go to another place. So our actuator understand in analog. So that's why we need digital to analog converter to make it the output analogs, and then understand the actuator. Of course, kalau kita guna motor pun, motor kita faham dalam volts. Okay, dalam volts. So the volt 0 to 5 volts reflect to analogs. Okay, so this is the analog. Understand the analog. So this is the generals understanding of using the ADC and DAC. Okay. Now we move to digital analog converter DAC. Okay. First, convert binary codes in BCD binary code decimals into analog codes in voltage or currents. Okay, our DAC, we want to convert the digital inputs here, D0, D1, D2, and D3 to analog outputs in voltage. Okay, so here we have D0, D1, D2, and D3. Okay, D0 is less significant bit, and then D3 is more significant bit. Okay, so they reflect, for example, 0, 0, 0, 1. Okay, 1 is more significant bit, and 0 here is less significant bit. Okay, this is the equations of analog output analog outputs for uh, BCD here. Okay, for example, we have BCD here. Okay, we have here. Okay, D0, D1, D2, and D3, and here this is a V out. Okay, or analog output. Okay, so the equation here is analog output equal to the resolutions multiplied by digital inputs. So the resolutions is equal to the step size and the less significant bits. Okay, so equation ni kena ingat lah. For examples, voltage resolutions 0.1 volts, digital input 10001, for example 0001. Okay, so we can use these equations, resolutions multiplied by digital inputs. Our digital input is 100 equal to 8 in decimals, so 0.1 multiplied by 8 equal to 0.88 volts. Now, number of bit, okay, we set as n. Number of level 2 power of n. Number of step in the outputs 2 power of n minus 1. For example, for 4 bit, so we have 4, n equal to 4. Okay, and then numbers of levels 2 power of 4. Okay, and then number of step in the output is power of 2 power of 4 minus 1. Okay, for 8 bit, we'll have 8 here, 2 power of 8, and 2 power of 8 minus 1. Okay. Okay, output voltage versus digital input DAC for 4 bits. Okay, if we look at here, we have the resolution 0.1 volt here. Okay. And then we have here 4 bits. Okay. We studied before. Okay. We studied before. Numbers of levels 2 power of n, and number of step in the output 2 power of n minus 1. Okay. Number of levels. Okay. Numbers of levels equal to 2 power of n. So n kita equal to 4. So equal to 16. So we have level here 16 from 1 to 6, 16. Okay, numbers of levels. And then numbers of step. Okay, number of step is 2 power of n minus 1. Okay, 2 minus n minus 2 power of n minus 1. So we have step here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So equal to 15 step. Okay, number of steps. Okay. If you look at here, V output Fs. Okay. V output Fs refer to V output full scales. Okay, we studied before. Okay, in order to calculate V out full scale, so we studied before V out equal to resolutions multiply with digital input. Okay, so the resolution is 0.1. Okay, for V out full scale means the maximum value lah. So we have the maximum value here is digital input 1111. So multiply with 1111 base 2, so equal to 0.1 multiply with, if we converts to decimals, become 15. So our V out full scale is 1.5 volts. So that's why our voltage full scale 1.5 volt here. Okay, volt here. Okay, we go for example 1. Okay, if voltage resolution 0.1, so digital input 101 base 2, calculate the V out. So we have the equations V out equal to resolutions multiply with digital input. Okay, so for the first examples, so 0.1 multiply with 1001, so equal to 0.1 multiply with, if we convert it, 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3. So kalau kita convert, kita akan dapat 1001 in decimals 9. Okay, 9. So kita akan dapat 0.9 volts. Okay, and then for the second questions, V out equal to 0.1 multiply with 1101 base 2. So 1101, okay, 1101 in decimals equal to 13, so equal to 1.3 volts. Okay, if you look at this 1001, okay, if you look at the diagram here, okay, 1101, so here, okay, 1101 here, if we go here, okay, 0.9 volts. Okay, it same like 1101. Okay, here 1101, here 1101. If we look at, oh sengit sikit, okay, 1.3 volts. Okay. Okay, now we go to example 2. Figure below show 3-bit DAC. Okay, sebelum ni kita tengok 4 bits. Dan kita tengok 3 bit DSC with resolution 0.5. So we have resolution 0.5 with 3 bits. Determine the step size voltage. Okay, determine the step size voltage. So step size kita dah tahu. Step size equal to resolution equal to less significant bit. So our step size voltage equal to 0.5 volts. Okay. Sketch and label the output voltage versus the digital inputs. Okay. So yang ni kita nak sketch yang ni lah yang kita buat sebelum ni. So sini V out kita. So yang ni daripada 0 0 0 okay until 1 1 1. Okay, input kita lah because of kita ada 3 bit. Kita ada 3 bit here. D0, D1 and D2. This is a V out. Okay. So kita boleh calculate ada solution lah. Okay. Tengok solution sini. So we have 0 0 0 0 and 1 1 1 1 1 1. Okay. So kita boleh calculate the maximum here. V out, we have V out equal to resolutions. Sorry, V out equal to resolutions multiply with digital input. So kita boleh calculate maximum value kita adalah V out full scale equal to resolution 0.5 multiply with 111 base 2. Okay. So 111 base 2 equal to 7s in decimals. So 0.5 multiplied by 7. So kita akan dapat 3.5 volt. So that's why our maximum value here 3.5 volts. Okay. So the resolution here is 0.5 volts. So N kita equal to 3. Number of step. Okay, number of step kita adalah 2 power of total step 2 power of N equal to 2 power of 3 equal to apa? 8. Okay, and number of step minus 1 equal to 7. Okay. So, number of levels sama seperti the maximum numbers of step 2 power of N, and numbers of step 2 power of N minus 1 equal to 7. Okay, and then voltage full scales kita akan dapat 3.5 volts. Okay. Then we move to percentage resolutions. This is another equation lah, second equation that we should remember. The percentage resolutions equal to step size or resolutions divided by full scales multiply with 100. Okay. So voltage full scale mana yang kita calculate tadi, step size multiply with digital inputs, but for full scales the digital input refer to the maximum is equal to numbers of step. Okay, so kita boleh simplify here. Full scale step size multiply with number of step. So kita boleh slash here. So become 1 divided by number of step multiply with 100. So number of step 2 power of N minus 1. So our resolutions here equal to these equations. So N refer to bits. Okay, how many bits. Okay, we go for example 3. For example, in 8-bit DAC have a step size 10 millivolts. So determines the percentage resolutions. Okay, so we can calculate number of step equal to, because of 8 bit. Okay, we have 8 bit, so 2 power of n, 2 power of 8 equal to 256 minus 1, 255. Full scale, step size multiply with number of step, 2.55 volts. So equation resolutions equal to step size divided by voltage full scale. So kita akan dapat 0.39%. Or we also can use the equations percentage resolutions equal to 1 divided by 2 power of n minus 1 multiply with 1/100. Okay, so 1 divided by 2 power of n minus 1 equal to 255 multiply 100. So kita akan dapat 1 divided by 255 multiply 100. Okay, so kita akan dapat also can get 0.39%. Okay, we move to example number 4. And 4-bit DAC have a step size 5 millivolts. So calculate the resolutions voltage. Okay, sama juga. We know step size equal to LSB, least significant bit, and also same resolutions. So calculate the resolution voltage 5 millivolt. Calculate the numbers of levels and numbers of step. So numbers of level equal to numbers of levels equal to 2 power of n. So kita ada 4 bit. So 2 power of 4 equal to 16 levels. And number of step equal to 2 power of n minus 1. Kita akan dapat 15 number of step. Okay, for digital input 1011, calculate the V out. So equation 5 millivolts resolutions multiply with 1 inputs 2. So 5 milli multiply with 1011 in decimal is 11s in decimal. So multiply 11s multiply with 5 milli. Okay, 5 milli. So kita akan dapat V out equal to 0.055 volts. Okay, number 4, calculate the full scale. Okay, V out full scale. Okay. V out full scales. So resolutions 5 millivolt multiply with the maximum number for 4 bit. Okay. So 5 milli multiply with 15. Okay. So kita akan dapat 0.075 volt. So determine the percentage of resolutions. So percentage resolutions equal to 1 divided by 2 power of n minus 1 multiply 100. sorry, 100%. 1 divided by 2 power of 4 minus 1. Okay. 1 divided by 15 multiply with 100. So kita akan dapat percentage resolution 6.67%. Okay. Okay. The importance of resolutions. The resolutions or step size or less significant bits of the DAC will determine how nearly the digital analog converters output resembles the actual analog values. And then the high numbers of bits will produce the small step size or resolutions new to actual analog values. Okay, for BCD, binary code decimal input code, the BCD is a code of 4 bits are used for each decimal digit of each code. We generate a 4-bit binary codes. BCD input that represent 2 decimal digits. For example, here, if we look at these diagrams, so we have BCD for less significant bit and BCD for most significant bits. So we have A0, B0, C0, and D0, and for A1, B1, C1, and D1s. So the range of inputs is 0, 0 to 9, 9s. For the step size is A0 at the less significant bits. Okay, for examples, D1, C1, B1, A1 is 0, 1, 1, 1, base 2. And then D0, C0, B0, A0 is 0, 1, 0, zeros. Okay, and then for the step size is 0.1. So V output, the equation of V output is step size multiply with digital inputs. So step size 0.1 multiply with here 0, 1, 0, 0 is 4, equal to 4 in decimals, and 0, 1, 1, 1 equal to 7 in decimals. So for the BCD, okay, for the BCD here is 74, and V out equal to 7.5 volts. Okay, examples 3 refer to figure above, figure here. Give the weight A0. Weight A0 ni equal to less significant bit lah. So A0 equal to 0.2, same with resolutions. We can call resolutions or step size lah. Okay. So determine, okay, step size equal to 0.2. Percentage resolutions. Okay. So percentage resolutions, we have 99. Okay, step size, because of the input digital range is 0, 0 to 99. So V full scale equal to number of step multiply with step size. Okay, so number of step maximum 99 multiply with 0.2 is 19.8 volts. So the resolution equal to step size divided by voltage full scales. Resolution 0.2, so divide by 19.8, so we get 1% resolutions. Okay, and then for the output voltage V out, if D1, C1, B1, A1 0, 1, 1, 0, 1, 0, 1 equal to 5, and D0, C0, B0, A0 is 0, 0, 1, 1, 3. So the digital inputs is 53. 0.2 multiply 53, we get 10.6 volts. Okay. Okay, that is BCD. Okay, now we go to digital to analog converter DAC circuits. We have 3 types of DAC circuits: resistor strings DAC, binary wake DAC, and R to R ladder DAC. Okay, the first, for the resistor strings. So the components of strings DAC, digital analog circuits, converters circuits, uh, supply the discrete voltage levels. So they have a selection switch to connect the right voltage level to OM according to the inputs bits. So the OM amplify the discrete voltage level to desired range, keep the current lows. Okay, so the numbers of resistors equal to 2 power of n here, and the number of switches switch 2 power of n, 2 power of n minus 1. Okay, so we have here B2 refer to less significant bit, and B0 refer to most significant bits. So this is a number of bits. Okay, for here we have 3 bits. Okay, for the resistor strings, to calculate our total, because of we have uh, uh, 8 resistance, okay, each resistor, so our total kita equal to 8R. So we want to calculate the I. Okay, V kita by using Ohm's law, V equal to IR. So I adalah V over R. So V kita ada V reference. So R kita adalah R total kita. So kita boleh calculate current yang lalu ni. So kita akan dapat R total kita 8R. Okay. Kemudian to calculate V is not here, for example here, so V1 equal to R1, so sini satu saja, Rn, divide by R total multiply with V reference. Okay, for example, V reference kita equal to 8 volts, so V3 here, okay, we have 3, 1, 2, 3 resistors with 1 ohm. So divide by 8. Okay, divide by 8. Multiply with 8 volt. So kita akan dapat 3 volt for V3. Okay. Now, for the selection switch. For example here, this is less significant bit. This is most sorry. This is most significant bit. This is less significant bit. Am I correct? Yes. Okay. So here, if you look at here, this is switch for zeros, and then this is switch for zeros, and then switch for zeros. So 0, 0, 0. So we get 0 volts. Okay, and then we have switch here 0, 0, and 1. So we get 0, 0, 1. Okay, so how many volts? Okay, how many volts? So V4 equal to 4 divided by 8 multiply by 8 volts. So kita akan dapat 4 volts. Okay. And then same. Okay. So these resistor strings have a disadvantage because of They are simple and fast for less than 8 bit. But for they also have a disadvantage, which is high element count for higher resolutions. The number of resistor to power of n. So kalau bit kita meningkat, so bilangan resistor dan bilangan switch juga meningkat. And then slow for greater than 10 bits. Okay. Now we move to another two standard of DAC converter, which is binary weight input and R to R ladder. Okay, both methods use the operational amplifier with negative feedback. In many applications, the OM's operational amplifier outputs is connected back to its inverter input directly or through the components, resistor or capacitor. This configure is called negative feedback. Okay. For binary weight resistor, okay, DAC, so the basic idea is use a summing operational circuit. So we have summing here, R1, R2 to R, R to R for R until 2 power of n based on bits multiplied by R. So they have a summing here. Use transistor to switch between high and ground. Okay, sini so kita boleh select by switching ni, kita boleh guna transistor. Use resistor scale by 2 to divide voltage and each branch by power of 2. Here. Okay, in a binary weight input DAC, the input current in each resistor is proportional to the column weight in binary numbering systems. So kalau kita tengok untuk binary weight ni, kita ada summing kat sini, D0, D1, D2 and D3. So D0 refer to less significant bit and D3 refer to most significant bits. So we have D0, D1, D2 and D3. For D0, the resistor 8R, D1 4R, D2 2R and D3 R. Okay. And then for the OM, okay, for the OM here, if you want to calculate the IF, okay, the IF, we get V0 equal to minus IF multiply with RF. So IF, if we doing some nodal here or KCL, okay, total current in equal total current out. So we get I0 plus I1 plus I2 plus I3 equal to IF. So kita boleh include dalam equation ni. And then I0, okay, here for I0 we using V equal to IR. Okay, so V adalah voltage pada D0. So I kita adalah VD0 for example, and then divide by the resistor equal to 8R here. For I1 same, divide by 4R, 2R and R. So we can include here. So our V out equal to minus VD0 divided by 8R plus VD1 divided by 4R plus VD2 divided by 2R plus VD3 divided by R multiplied with RF. Okay, we go to examples. The certain binary weight input DAC have a binary inputs. Okay, kita ada binary inputs 1101. If the high equal to 3 volts and low equal to 0 volt, resistor 15 ohms, what is V out? Okay. We have 1101. Okay, we have 1101. This is D0, D1, D2, and D3. Okay, we have here for binary weight for 8R. So we have this is D0, D1, D2, and D3. Okay, so our circuit become like this lah. Okay, so in order to calculate I out, okay, I out sini, okay, sini IF equal to I0, I1, I2, and I3. So we get here I out. Okay, and then to calculate V out, so we know V out equal to minus IF, sorry, V out equal to IF minus IF RF. So IF ni equal to I out. Okay, so 0.325 milli multiply with 10k, so kita akan dapat minus 3.25 volts. Okay, we go to another examples. Determines the output voltage V out digital analog converters binary weight in figure below. If given the wave of the input sequence of the number that represent 4 bits, we have 4 bits. Given D0 is a less significant bit and D3 is a more significant bit, assume that the input voltage 5 volts digital when the condition high and 0 when condition low. Okay, here the current flow to each resistor we can calculate for I0, I1, I2, and I3 by using V equal to IR. So I0 equal to 0.025 milli and until I3 0.2 milliampere. And then for the output voltage V out, when the digit inputs V out equal to minus RF I out. Okay, and V out for D0 equal to minus RF multiply with 0.25 equal to minus 0.25. And then the output voltage when the digital input is 0010. So we also use the same equations. So kita akan dapat minus 0.5. And when the digital input 0100, so kita akan dapat minus 1. Until then for 100 kita akan dapat minus 2. So we can plot these tables for digital inputs in binary weight from 000 to 1111 as a digital inputs, and V out is the digital the analog outputs. So the binary weight resistor DSC simples and fast, but for the disadvantage need large range of resistor value for 12 bit, for example, with high precision in low resistance values, and needs very small switch resistance. Thank you. Okay, now we move to R to R ladder DSC. So this is the circuit for R to R ladder DSC. This R to R consists of resistor R and 2R. So that depends on the number of bits yang kita gunakan lah. For example, for this DSC, there are 4 bits. Okay, macam mana kita nak tahu 4 bit? Kita tengok dekat negative feedback OM here. Kat sini ada, ni adalah negative feedback. Okay, negative feedback OM. Okay, so dekat bahagian negatif sini, okay, kat bahagian negatif sini, dan ni adalah bahagian positif, kita sambung ke ground. So bahagian negatif ni kita tengok, kalau kita punya R to R ni bersambung dengan bahagian negatif ni, dia akan jadi high. Okay, high, satu line ni. So kalau dia bersambung dekat bahagian ground ni, so dia akan jadi low. Okay, so kita nak tahu how many bits, dia depend on switching kat sini lah. 2R kat sini. 2R ni kat tengah ni. Okay, so kalau dia sambung 2R kat sini, dia akan jadi positif. Dia akan jadi high. So kalau dia sambung kat sini, dia akan jadi low. So we have 1, 2, 3, 4. So it means that 4 bits. And they start from here, D0 with less significant bit and most significant bit. So dia akan susun D0, D1, D2 and D3 lah for 4 bit. Okay. Untuk 4 bit, they are using 3 resistor R and 5 resistor to R. Okay. And 4 current switch will be activate depending on the input digits. So kalau kita tengok, kita ada kat sini R1, 2, 3 dan juga 2R kita ada 1, 2, 3, 4 and 5. Okay, we do some analysis. Okay, we look at the not 0 here. Okay, the not 0 here. So if we want to calculate the R0 here, so R0, so kalau kita draw, so sini adalah 2R and then kat sini adalah 2R. So kalau kita nak calculate R0 here, so R0 equal to 2R parallel with 2R. So kita akan dapat R lah. Okay, R0. So that's why R0 equal to R. Okay, now if you want to calculate at this not 1. So kalau not 1 ni kita calculate, so kita akan ada 2R kat bawah dia, 2R. Dan kita ada R, and then kat sini kita akan ada R0 yang sebelum ni. So kat sini kita nak measure R1. So R1 kita equal to 2R parallel with R plus R0. Okay, and then R0 kita adalah R. So equal to 2R parallel with 2R. So kita akan dapat R. So that's why R1 equal to R. Okay, and then kita tengok yang seterusnya. Untuk R2, okay, dekat node yang kedua ni sama juga. So kalau kita draw, kita ambil dekat R2. So kalau kita draw, sini adalah 2R. So sini adalah R, and then sini adalah R1. Okay, sini adalah kita nak tengok dekat bahagian R2. So equation yang sama, R2 equal to 2R parallel with R plus R1. So R1 kita equal to R. So 2R parallel with 2R. So kita akan dapat R2. Okay, so kita dapat R2 here. And then R3 pun sama kat sini. So untuk measure R3, so kita akan dapat R3 equal to R. Okay, and then kita tengok dekat bahagian supply V reference here. So by using Ohm's law, V equal to IR. So I equal to V divided by R. So kat sini V reference. So R yang lalu kat sini adalah R total ni lah, ataupun R3. Okay, dan R3 kita equal to V reference, R3 kita equal to R. So that's why equation kita akan jadi I reference ataupun I kita adalah sama dengan V reference divided by R. Okay. Now, kita tengok one by one dekat nodes yang kita dah buat tadi. I3. Okay. Kita tengok dekat nodes 3. Okay, kita tengok dekat nodes 3. So kalau kita draw sedikit, so yang masuk adalah I ataupun I reference. I reference ataupun sama dengan I lah. Okay. So dia ada node 3 kat sini. So dia ada resistor R and resistor R2. Okay, sini adalah 2R. So R plus equal to R. So samalah. So current yang kat sini akan sama dengan current yang keluar. Yang masuk total current in equal to total current out. Okay. KCL punya rule kan. Okay. So kita boleh buat. So I3 kat sini. I3 kita nak calculate ni. Kat sini masuk sama dengan I3, I3. Okay, IF sama dengan I ataupun sama dengan I. So I3 yang kita nak calculate ni adalah I divide by 2 lah. Okay, so yang kat sini yang akan lalu adalah I3 equal to I divide by 2. Okay, and then kita nak calculate kat sini pula I2. Okay, kita nak calculate kat sini I2. So sama juga, resistor into R plus R, R plus R. So resistor ni sama, so I2 equal to I3 divide by 2. Okay, I2 equal to I3 divide by 2. So masukkan I3 ni, I divide by 2. So akan dapat I2 equal to I divide by 4. And then sama juga dekat note kat sini, kita boleh calculate I1. So I1 here, I1 adalah because of the resistor same to R. So I1 equal to I2 divide by 2. So yang masuk sini adalah I2. So that's why kita akan dapat yang ni. So kita masukkan semula I2 equal to 1 divide by 4. So kita akan dapat I1 equal to 1 divide by 8. Okay. And then we go to the last point here. Last note. So I0. So we calculate the I0 here. I1 divide by 2 because of the same resistor to R and to R. So kita akan dapat I1 divide by 2. So kita gantikan I1 I divide by 8. So kita ganti, kita akan dapat I0 equal to I divide by 16. So this I0 is a less significant, kita boleh katalah dia less significant bit sebab dia kat bahagian ujung. Okay. Cuma kita boleh dapatkan I0 ni adalah current resolutions. Okay. Ataupun kita panggil sebagai step size. So kalau kita tengok 2 power of 16 dia sama seperti I divide by 2 power of 4. Okay. 4 ni reflect kepada bits number. Okay. So means 4 bit. Okay. So the current resolutions equal to I ni kita boleh gantikan yang kita kira tadi, I equal to Vref divided by R. Okay, kita dah calculate tadi, I yang depan ni adalah Vref divided by R. So kita gantikan, so kita akan dapat current resolution equal to Vref divided by R multiply with 1 divided by 2 power of 4. So to calculate the I out here, so kalau kita nak calculate I out here, so I out adalah current resolutions, okay, current resolutions multiply with digital inputs. So 1 divided by I divided by 16, or ni Vref divided by R multiply 1 over 2 power of 4 multiply with digital input. So we can calculate the I out. Okay, and then to calculate the V out, tadi kita dah dapat I out. So to calculate the V out, so V out equal to negative I out multiply with RF. Okay, so V out equal to, kita gantikan I out kita adalah V reference divide by 4, V reference divide by R multiply with 1 divide by 2 power of 4 multiply with digital inputs multiply with RF. Why negative? Because of this is the negative feedback ohms. So V out kita sama juga equation, equal to negative voltage resolution darab multiply with digital inputs. So the voltage resolution kita equal to V this. Okay, this is our voltage resolutions. So current resolution don't have RF lah. So voltage regulation we have RF. Okay, now we go for the example. Okay, refer to the 4-bit R to R ladder DAC. V reference equal to 5 volts, R equal to 10 kilo ohms, and RF equal to 5 kilo ohms. Now calculate the current resolutions. Okay, current resolutions kita dah tahu sebelum ni adalah V reference divided by R multiply 1 over 2 power of N. So because of bit kita, number of bit 4, so kita calculate and then kita akan dapat 0.031 milliampere. And then second, calculate I out when digital input 11001. Okay, so kita dah tahu I out equal to current resolutions multiple with digital input. So kita akan dapat okay, so kita convert 1101. This is in binary, so we convert into decimal. So kita akan dapat 0.403 milliampere. And then next, for voltage resolutions, so we just add RF here. So kita akan dapat voltage resolutions kita equal to 0.156 volts. And then V out kita, bila mana kalau kita tengok, this will calculate V out for D, V out when digi input 1001. So kita just use the equations, minus voltage resolutions multiply with 1001. So convert to decimal 9. So kita akan dapat minus 1.404 volts. Okay. Okay, now we go to the exercise. Okay, we go to the exercise 1. Determine the resistance RO. Okay, RO here. So kita ada RO kat sini. Okay, so kita nak determine RO. So kita boleh buat apa? Satu-satu kita buat dekat not 0, not 1, not 2, not 3, not 4, not 5. Okay, kita boleh buat set satu not. Cuma kita dah tahu R to R ladder, this is R to R ladder. Okay, R to R ladder. So kita tahu R out kita yang paling hujung ni, untuk kita tak nak calculate lah, equal to R. Dia equal to R ataupun equal to 5 kilo ohm. Ataupun kita boleh buat analisis lah. Okay, and then the voltage resolutions. Okay, voltage resolutions untuk R to R ladder ni, voltage resolutions equal to V reference, okay, divide by R, 1 divided by 2 power of N. N is a big number and multiply with RF. Okay, so we reference kita berapa? 10 divided by R kita 5K multiply with 1 over 2 power of, okay, sekarang ni kita berapa bit? Macam mana kita nak tahu berapa bit? Kita tengok kat sini, dekat switching sini. D0, D1, D2, D3, D4, D5. So kita ada berapa? 6. So it means 6 bit. Okay, multiply with RF. RF here, this is RF 5K. So kalau kita calculate voltage resolution kita, kita akan dapat lebih kurang 0.15625 volts. Okay. Now kita continue outputs. Okay, now kita nak kira output voltage if sekarang ni jika connection kita adalah 110101. Okay, so kita tahu V out kita okay, V out kita, V out equal to voltage, V out equal to voltage resolutions multiply with digital input. Okay, ni equation yang kita kena ingat selalulah, negatif. Okay, untuk R to R, untuk R to R ladder. Okay, so voltage resolution kita dah calculate tadi, okay, ni negatif yang equation yang asal, 0.1615625 multiply with 110101 base 2. Okay, so kita akan dapat 0.15625 multiply with 53. So untuk convert daripada binary kepada decimal, boleh guna calculator. So nak guna calculator, bila kita on calculator, kita tekan mod, and then kalau kita tengok kita ada number 4 tu base n. Okay, and then kalau tengok dekat dalam tu kita boleh pilih sama ada kita nak decimal ataupun binary lah. So masukkan number binary berapa, 11001. So convert kepada decimal, akan dapat 53 lah. Okay, and then kita akan dapat minus 8.28125 volts. Okay, so itu adalah Vout untuk Vout untuk exercise 1. Okay, kita pergi kepada last exercise kita. Determine the analog output voltage based on the position switching given below. Okay, so kalau kita tengok this figure, kita nak calculate Vout. Okay, so kita tahu equation Vout minus voltage resolutions multiply with digital input and input. Okay, so first kita tengok dulu digital input kita macam mana. Okay, kita tengok yang negatif ni. So negatif ni dia boleh jadi sini 1, sini 0. Okay, dekat negatif sini 1, sini 0. Sebab apa 0? Sebab dia sama kepada ground tadi. So sini 0, sini 1. Sini 0, sini 1. Dia terbalik kan tadi. So ni trik sikit. So kena make sure lah. Ada soalan, kena tengok betul-betul. Bukan mesti belah kanan tu 1, 1, belah kiri tu 0. Dia tak semestinya. Okay. So kalau number kat sini kita boleh tengok ni adalah less significant bit. Sini adalah most significant bit. Okay. So sini adalah 0, sini 1. So kalau kita tengok 1, 0, 1, 0, 1, 0, 0. Base 2. So ni adalah digital input yang ada berapa bit? 5 bit. Okay. So first kita nak kena calculate voltage resolutions. Okay. Untuk voltage resolution kita dah tahu equation voltage resolutions. So contohnya voltage resolutions equal to V reference divided by R multiply with 1 divided by 2 power of N multiply with RF. Okay, multiply with RF. So V reference kita 10, R kita berapa? 10K. 1 divided by 2 power of 5. RF itu berapa? 10K. Okay. So kita kalau kita tekan calculator, sekejap saya calculate first. So kita akan dapat 10 divided by 2 power of 5. So kita akan dapat 0.3125 volts. So untuk calculate Vout, kita akan dapat minus 0.3125 multiply with 10100. So kalau kita convert daripada this binary, kita akan dapat minus 0.3125 multiply with 20. So kita akan dapat multiply 20 6 minus 6.25 volts. So this is the output voltage based on the position given for exercise 2. Okay, and then for the R2R DSC summary, so the advantage of this R2R, only two resistor value, R and 2R, easy to manufacture, faster response time. And disadvantage is more confusing analysis. Kalau kita nak buat analysis lah, macam kita nak buat pembuktian R1 equal to 1, R2 equal to R, R3 equal to R, situ ada bit confused lah bila kita buat banyak bits. Okay. Jadi itu saja untuk chapter 1. Thank you.